Swayam Prabha. Digital India. Educated India.
Welcome to Concrete Technology, Module 3, Lecture 2. We shall be continuing with chemical admixtures. If you recall, last class we talked about water reducing agent, and then we said you can use the water reducing agent to minimize the cement consumption at a given workability, increase the workability at a given level of strength, and use the water reducing agent simply to increase the workability alone. So, we continue with that, then we shall look into retarders and accelerators, air entraining agent, viscosity modifier, corrosion inhibitors, waterproofing admixtures and anti shrinkage admixtures. So, continue from the last class. If you recall, we looked into this a diagram which showed that we can use it in different way. For example, this is somewhat repeated in a slightly different manner in this diagram. In this axis, if you see, we have water content, and then in this axis is flow table stable spread, right. Now, this is flow table spread, all right. So, if you use without superplasticizer, you want to increase the flow table spread, that is the workability, you shall be increasing the water content. So, you increase the water content, the flow table spread will increase, increase the water content, flow table spread will increase, all right, like this. This is the curve. But if you add superplastic, but supposing at the same water content you want to get higher flow, then simply increase the add superplasticizer. So, with superplasticizer at same water content you can get higher flow, but supposing you want to maintain the flow same, then you can reduce the water, and if you want to maintain the same strength, you can reduce down the cement also. So, you can have a cement saving, but you want to get higher strength, keep the cement same. So, recall from the previous diagram, it is something similar. So, superplasticizer can be used to increase the workability at a given strength without adding any more water. You can increase the strength for the same workability by reducing the water content and keeping the same cement same, and also you can keep the water content same. You can reduce down the water content, you can save on cement content by reducing down the water content and reducing down the cement as well. So, you can save on cement at the same strength and workability if you like. You can get higher strength at same workability, or at same strength you can get higher workability. So, this is the way one can use superplasticizer. Well, it is important to look into superplasticizer compatibility. That means, it must give the superplasticizing effect. The superplasticizer must give the superplasticizing effect, all right. Set retardation could be some issues. That means, depending upon the sugar content of the sugar content of the superplasticizer, and at higher dosage it may be pronounced, higher dosage it may be pronounced. Of course, it depends upon cement type, because interaction of the cement is very important. It depends upon the cement type. All right. There can be some secondary effects. Okay. For example, if you do overdosing, this can result in bleeding and setting delay. It can result in high bleeding. A lot of excess water might come out of the system and result in bleeding, and setting delay can also be there. Setting delay can also be there. So, one has to look into those. No overdosing and right kind of compatibility should be seen. In fact, if you go on increasing the dosage of the superplasticizer, beyond a point it will not show any further plasticizing effect. There is a point of diminishing return. So, the dosage, maximum dosage is added such that beyond that, if you increase further, you will not get any further plasticizing effect. So, that is the maximum, and you should not have any kind of negative effect. Water cement ratio less means bleeding will be reduced, and you will get strength improvement as well. So, that is right, and reduction of water reducing effect due to consumption of SO3 by C3A. This can be an effect. For example, sulfonated superplasticizer or plasticizer, sulfonated compounds, they might react with high C3A cement, C3A in case of high C3A cement, and water reducing effect may be reduced. So, because it is sulfonated compound, if you recall that SO3 gets as it is SO3 sulfonation was done. So, you will have sodium plus and SO3. So, sodium goes into solution, SO3 ensures that it is negatively charged. Your superplasticizer is negatively charged and it can get absorbed, but supposing the SO3 is consumed by C3A, excess C3A being present in the cement, then reduction of water reducing effect could be there. So, type of cement also matters. Some accelerating effect is seen from superplasticizer, because they can disperse the, since they disperse the particle, you can see that with superplasticizer dosage, higher the dosage, right, with higher superplasticizer dose, you have strength. No, zero superplasticizer, if this was the compressive strength, with higher dosage strength, early strength increases, 12 hour strength, 24, but 28 day strength, there is of course much less influence. So, this is because better dispersion of the system, that is because better dispersion of the system. So, it has got somewhat an accelerating effect, because hydration will get accelerated, more dispersion, more particles will come in contact with water and resulting in better better hydration process, more uniform hydration product, and that is what you have got somewhat accelerating effect of the superplasticizer. Well, after time loss, if you see there is slump loss, or in other words, if you look at slump retention of water reducing agent. Now, this is important because of, in case of ready mix concrete, you would like to deliver the concrete after maybe certain period of time after mixing, because it will be there in the agitator track. So, in such situation, slump retention is an important parameter or factor. That means, it should remain green, or it should not set. So, setting time of the concrete here is important, and supposing you have control, this is your control concrete without anything, control concrete is this is your control concrete. So, control concrete is here. So, here a slump, and this slump became practically 0 after, let us say, some time, say 100 minute after mixing, 125 minutes or 20 minutes after mixing. Now, you have plasticized one, that is this line, just plasticized. So, initially it is high, obviously it is retained for also longer period of time, but if you have a plasticizer come retarder, it is still retained for a longer period of time. So, it is nearly doubling up the time when slump becomes 0, but anyway you might be requiring some fixed slump. So, it can retain for longer period of time, right, retarded with, this is with plasticizer, but if you have super plasticizer, So, then slump itself in the beginning is very high and it is retained for longer period of time. Note that slopes in these cases are more or less similar. So, the fact that you have high slump in the beginning, right, you have high slump in the beginning. So, as the time passes, the loss of slump rate is same, but it can retain for longer period of time. So, is a useful thing as far as ready mixed concrete is concerned. You have now more time for placing, no adverse effect on concrete in any case. So, loss of slump with superplasticizer, as we have seen, is somewhat lower. Well, hydroxylated carboxylic acid type may increase bleeding in high workability, and lignosulfonic ones improves cohesiveness by entraining air. So, these are some secondary effects. Hydroxylated carboxylic acid type, all right, may increase bleeding in high workability. These are polycarboxylate and similar ones. Bleeding in high workability can be seen in this kind of thing, and lignosulfonic acid ones may improve the cohesiveness by entraining some amount of air. Rate of hydration is obviously likely to increase, and long term strength also may be improved. Long term strength also may be improved. Low C3A, low alkali cement usually have more influence. Low C3A and low alkali cement usually have more influence. All right. So, C3A should be low, because as we have seen many cases, alkalis and C3A, they can interfere with the superplasticizer's action, and thus it is better that you have low C3A and low alkali cement. So, this was water reducing agents, plasticizers, superplasticizers and hyperplasticizers. Now, we can come to retarders, the another kind of admixtures, and we defined perhaps the one which will retard the setting and hardening process. Let us see what they are. Essentially, retarders extend the time for the mix to change from plastics to hardened state, or harden, of course, solid state, first to solid and then hardened state. So, solid state, it requires more time. Typical dosage would be 0.2 to 0.6%, and examples are molasses, sugar, gluconates, sucrose, some phosphates. So, they are the retarders. In fact, sugar is a good example. Supposing your machine is stuck and you are not able to, or your agitator truck is stuck in traffic, and you know that you won't be able to reach the site in time, and actually it will set by the time you reach, because it is in a traffic jam or something like that. Well, if you put some retarder like let us say sugar sufficient amount, it will never set. So, it is called killing of concrete. Concrete mix can be killed actually. So, it will never set. So, they are retarders. Temperatures do have some effect. Temperatures do have some effect on the retarding action, and this should be seen. This should be seen. This should be also considered. So, temperature has some effect and shall be accounted. Higher temperature, first reaction takes place, retarding action will be less. These are common in RMC, as I said, because plasticizer cum retarder is usually plasticizer cum retarder. These are usually common in ready mixed concrete. Ready mixed concrete, RMC stands for ready mixed concrete, because you want long time, somewhat longer slump retention, because when you want to deliver the concrete at the site, the time required may be slightly higher, and therefore, you like the slump to be retained, and that is why you use retarder cum obviously plasticizer to minimize the water content, water required, hence save on cement for the same strength. The retarders, the processes involved or the mechanisms, if you look at it, blocking mechanisms, where blocking mechanisms where actually admixtures is adsorbed on the surface strongly on the cement surface and slows down the formation of silicate hydrates. So, that is the thing. So, basically they can be adsorbed onto the cement surface, and therefore, formation of silicate hydrates is stopped because they are adsorbed on the surface, right, and strongly, and therefore, slows down the process of formation of silicate. A second mechanism could be chelation by admixtures of calcium ions in solution. Basically calcium ion, two organic molecules can form a complex with calcium, right, with calcium ion. So, the retarders compounds, organic compounds in the retarder can form complex with the complex with the calcium ion, and therefore, prevent precipitation of calcium hydroxide, prevent precipitation of calcium hydroxide, prevent precipitation of calcium hydroxide. So, that is what it is. So, calcium hydroxide precipitation is prevented. Now, if calcium hydroxide cannot precipitate, therefore, the reaction cannot go in. So, reaction cannot, because calcium silicate hydrate formation needs calcium silicate formation, hydration formation needs calcium hydroxide production. Reaction of calcium has C3S and C2S forms calcium hydroxide and calcium silicate hydrates. Now, if calcium is not precipitating, these two reaction cannot proceed. So, that could be another mechanism or both. So, both these mechanisms may be at work, but later one is just retarder without plasticizing effect. First one is with plasticizing effect, that is coating on top of the surface. So, this coating might also disperse the particles, cement particles, while the second case will not have this calcium ions forming complex will not have plasticizing effect, right. Retarding admixtures delay the end of dormant period. Dormant period, we saw it earlier sometime. Dormant period means the period during which attringite is largely formed. First 30 minutes attringite is formed, right, and CHS formation really do not start. So, this essentially ensures that longer attringite period, longer dormant period, and therefore, setting is delayed, all right, and after that setting starts and followed by hardening. Good, useful in avoiding cold joints and slip form concrete, etc., etc. Slip form construction is continuous construction of vertical members, chimney, or even buildings, walls and things like that, vertical members, right. So, continuous casting can casting goes on continuously. Now, cold joint is formed between hardened concrete and fresh concrete, because they do not bond well. So, if you have longer setting period and you have put in a layer of concrete and you want to put in the next layer of concrete, if you have a longer setting period, you are putting fresh concrete over unset concrete, it will ensure that there is no cold joint formation, because they will bond better. So, bonding is better if the setting time is longer. So, you are pouring the concrete already unset concrete, not set concrete. So, there will be no cold joint formation. Well, that was one class, and just similar to this is the accelerator, which is another class of admixtures. Now, accelerating admixtures are divided into two groups, one is set accelerating, another is hardening accelerator. Set accelerating and hardening accelerator. Now, set accelerating means it will enhance the setting time, shorten the setting time. Hardening accelerator will mean that it will increase the early strength gain. So, set accelerating and hardening accelerator, there are two varieties. The set accelerator reduce the time of transition from plastic to solid state and extent varying as required. Extent would be as required, how much you want, that would as you want. Hardening accelerator enhances the rate of strength gain, that is what I just said, early strength you can get from here. Now, generally dosage varies from 0.5 to 2% on cement and usually are inorganic compounds. They are not organic formations, inorganic compounds. Calcium chloride used to be one of them. It is the most effective accelerator and can act as both set and hardening accelerating admixture. So, setting as well as hardening process it can accelerate, right, the calcium chloride, but unfortunately calcium chloride is a problem from the durability of reinforced concrete, because it will initiate the rebar corrosion process by what is known as depassivation of the steel. So, usually some kind of passive layer forms over steel which protects the steel, but if calcium chloride is present, such passive layers get broken down and it is called depassivation, and it is not preferred. That is why. So, if you have embedded steel in concrete, calcium chloride is not the preferred admixture that would be used. So, in fact, it is not used anymore. Chloride free accelerators are what is preferred. These are nitrite, sodium or calcium nitrate or nitrite, formate and thiocyanates. So, chloride free accelerators like sodium or calcium nitrite, nitrate, formate and thiocyanates are useful in this direction. As we have seen earlier, high range water reducing agent has some accelerating effect, hence are effective with accelerator in combination. So, use the accelerator, come the superplasticizer, high range water reducing agent, this will have an accelerating effect, right. They themselves have some accelerating effect, and if you use together with an accelerator, the benefit is even more. It is more effective, it is more effective, it is quite effective, it is quite effective, all right. Set accelerator possibly accelerate the formation of ettringite, because you see if ettringite formation is faster, dormant period will be reduced. So, set accelerators possibly accelerate the formation of ettringite, because we know during the initial phase of setting ettringite is produced during the dormant period. During the dormant period ettringite is produced and it accelerates the setting process, it accelerates the setting process, all right. It accelerates the setting process, it accelerates the setting process, all right. It accelerates the setting process. Hardening accelerator increase the rate of dissolution of calcium silicate. Hardening accelerator accelerate the rate of dissolution of calcium silicate and therefore, increases CHS formation as early age, all right. Hardening accelerator accelerate the CHS dissolution of calcium silicate and therefore, calcium silicate can react faster and thus early CHS formation can take place. So, that is how early strength you can get. High range water reducing agent enhances hydration and homogeneity, that is what we have seen earlier, thus useful in accelerating water reducing action. So, we have seen that they are good in accelerating water reducing action, all right. Well, it would be useful where we want early deshattering, pre-stressing is required. So, you want to do pre-stress, it should have sufficient strength gain, because pre-stressing can be done. If you want to remove the mold early, strength gain should be sufficient, and then only you should do pre-stressing or remove the mold. So, hardening admixtures accelerators are useful where early deshattering, pre-stressing is desired. So, this was the second variety. There are two varieties that we have seen other than water reducing agent. One is the retarders and the second one is the accelerators. Now, the third variety is air entaining admixtures, largely used for freeze thaw resistance. We shall be looking at that when we look at durability of concrete, largely used in case of freeze thaw to improve the freeze thaw resistance of concrete, right, freeze thaw resistance of concrete. So, essentially what they, how do they act? They essentially essentially these ones, they entrain the air bubbles into the concrete, and this air bubble in turn cause release of hydraulic pressure generated by frost action. We will explain this process in details later on, but at the moment let us understand what these are. So, these admixtures, if you put controlled quantity of small uniformly, it actually puts in, makes it actually forms small uniformly distributed air bubble, small uniformly distributed air bubbles that is introduced into the concrete during mixing, and they remain also, they also remain after hardening, they remain also after hardening. So, that is what it is. So, air entraining admixtures, they allow for small uniformly distributed air bubbles to be introduced during mixing and remained after hardening. The dosage is usually 0.2 to 0.4% on cement, dosage is usually 0.2 to 0.4% on cement. Well, they do not foul with the performance of dispersing admixtures, that is our water reducing admixtures, right. Now, may contain only 1 to 5% solid, thus very powerful, and let us look at principle, how it works. Obviously, if you are introducing pore, one issue is that strength would be reduced, So, if you introduce pores, strength would be reduced, strength would be reduced 5 to 6% reduction when you have added 1% for each 1% of additional air. So, you add 1 more percent of air, 5 to 6% reduction in strength will occur. Mainly, as I said, used for freeze thaw resistance, mainly for freeze thaw resistance. How does it do it? Mechanism. Well, we will see that, but improves cohesion and reduces tendency to bleed. That is of course, a little bit of air entrainment actually improves the workability, that is a side effect. Basically, it improves the cohesion within the concrete, and tendency to bleed is reduced because it can retain the water more. So, naturally easy compaction is possible at lower workability. So, essentially it improves the workability of the mix, it increases also the workability of the mix. Interior stability of any kind of extruded concrete, anything extruded through extruded or anything, any concrete placed through compressed air, pneumatically placed concrete. So, it improves actually stability of such concrete. Basically, they are surfactants, that is the mechanism, surface acting agents, and they are organic compound, right. As you can see, they are organic compounds. There are two types, they are both amphiphilic and hydrophilic. What is amphiphilic? Amphiphilic, which means that they have got hydrophobic and hydrophilic, both. Hydrophobic tails and hydrophilic heads. What is hydrophobic? Which will push the water away, reject the water. Hydrophilic goes well with the water. Since they are hydrophilic, therefore, they are soluble in water and they are also soluble in organic solvents. So, they are amphiphilic, that is hydrophobic and hydrophilic, resulting in amphiphilic resulting in hydrophobic and hydrophilic both. So, tail is one tail is groups tails are hydrophobic and the head is hydrophilic. So, something attracts it long in a kind of chain. On one side they have got molecules which can attract water, another side molecules which can reject water. Thus, they exhibit hydrophilic, water loving and fat loving properties, lipophilic, fat loving properties. So, hydrophobic group, some of them show lipophilic or fat loving properties. So, this is are the two things. Essentially, they reduce the surface tension of water by adsorbing at the liquid gas interface. So, they get actually adsorbed at the liquid gas interface, that is water air interface, all right, and change the surface tension properties of the water, surface tension properties of the water. In fact, the charged hydrophilic and remains in water and hydrophobic tail traps air bubble. So, therefore, they are at the boundary of water and air interface, at the air water interface they would be there. In the water side, the charged part, this remains in contact with water, the hydrophobic tail traps air bubble, all right. So, at the interface, actually in this process they increase the surface tension of, reduce the surface tension of water and bubble formation becomes easy. So, easy formation of air cavity or bubble as work required to produce unit area of liquid gas interface is lowered, right. So, easy formation of bubbles, because easy formation of bubbles as work unit area and work required to produce unit area of liquid gas interface is lowered, right. Liquid gas interface is lowered. How much is this work? In a bubble, the pressure inside in a bubble, the pressure inside pressure must be balanced by the outside pressure. Inside pressure must be balanced by outside, that must be balanced, and it is actually P in is given as P in is equals to P out. Outside pressure would be P outside pressure plus twice gamma by R, because inside the bubble there is at the interface the surface tension, the water is there at the interface. So, water is there at the interface, this is the air bubble, water is there at the interface, So, at this you can show that the pressure here is twice gamma by R. So, P outside is P out plus 2 gamma plus R is equals to P inside, otherwise the bubble will collapse. So, bubble should have sufficient pressure inside, P inside must be sufficient such that it can balance the outside pressure and the pressure due to surface tension forces. The work done would be to increase the surface area by dr. It was 4 pi r square, now the area will become 4 pi r plus dr square, and which will be 4 pi r square plus 8 pi r dr plus terms involving 4 pi dr square, which can be neglected, this can be neglected, and therefore, increase in pressure. So, delta W will be given by dW will be given by this. So, dW is given by this, So, pressure. So, if the surface tension is reduced, less work is required. If surface tension is reduced, less work is required to maintain the surface. In fact, this will also get reduced. Therefore, outside pressure at outside P inside pressure is equals to P out. So, this itself will get reduced. The possibility of bubble formation actually increases, So, easy formation of air cavity or bubbles as work required to produce unit area of liquid gas interface is lowered when surface tension is low. Generally, hydrophobic groups is generally are fats, oils, petroleum fractions. Hydrophilic ones are carboxylates, they are carboxylates, sulfates, sulfonates and phosphates, right. So, these are the ones. largely salts of wood resins, synthetic detergents, salts of petroleum acids, and fatty and resinous acids and their salts. So, these are the materials: salts of wood resins, synthetic detergents, salts of petroleum acids, etc., fatty and resinous acids and their salts. For example, bean salt resin is obtained from pine wood. Bean salt resin is an aliphatic hydrocarbon extracted from pine wood. Stumps is pine wood stumps is the common source of air entering agent. So, it is from the bean salt resin is one which is obtained from pine wood, and that is used, that is the common source of air entering agent. So, we said that salts of wood resins, therefore, this is one of the example. So, what we have seen, that is air entraining agent which reduces the surface tension, but then we have another variety called viscosity modifier. Now, viscosity modifying agent are viscosity modifying modifiers are water eating, they are used in underwater concreting anti washout admixtures. They are essentially anti washout admixtures, and they have high molecular weight, they are soluble polymers. So, cellulose ethers, alginates and polyethylene oxides increase the viscosity of water by interacting through hydrogen bonding. Cellulose ethers, they are basically something like, crudely we can understand something like gum. A gum you put in water, it will increase viscosity. So, some of those materials increase the viscosity of water, and therefore, then it can hold on water and the cementitious material together more easily. So, they form open branch polymer network in water and essentially lock the water and the cement and sand particles, reducing viscosity and increasing the cohesion. So, that is the idea, they lock the water, cement and sand, reducing viscosity and increasing cohesion. Dosage may be ranging from 0.1 through 0.3 to 1%. So, dosage may range from 0.3 to 1%, all right. Dosage may range from 0.3 to 1%. So, these are viscosity modifiers used in underwater concreting, and nowadays in some of the self compacting concrete. Some of the self compacting concrete uses this material, because when you use polycarboxylate ether slightly in larger quantity, it has a tendency to bleed, as we said, can cause bleeding. But if it has got tendency to bleed, one way you can stop is by using a lot of fine particles which can hold it together, use of very fine materials which can hold it together. So, very fine like cementitious or inert material which can hold it together, right, and that is viscosity, or else you can use viscosity modifier which will also block the water, cement or cementitious material and sand together. So, bleeding would be reduced. That was viscosity modifier. Then we have got corrosion inhibitor. They can stop the corrosion process, because rebar corrosion is one of the major problem, one of the major durability problem in concrete, and corrosion inhibitors stops this, corrosion inhibitor stop this, corrosion inhibitor stop this, all right. How do they do it? They actually can block anodic or cathodic reactions. Examples of these are nitrite, calcium nitrite, chromates, molybdates, amino alcohol and blended with inorganic inhibitors. Calcium nitrite, chromates, molybdates, amino alcohols and amino alcohol blended with inorganic inhibitors, they are the ones, they are the examples of corrosion inhibitors. they can act in two different ways, may increase the corrosion threshold, right. So, the point at which corrosion, active corrosion starts, they may just increase that, they might delay the starting of corrosion. Nitrites helps in making what is called a passive layer, more stable. Now, a passive layer is the oxide coating over iron or rebar, which protects the steel, because steel you can't, iron is not a stable thing, it will get oxidized. But if it does not get oxidized to at a very fast rate or to a product which is dangerous, then it is tolerable. So, dense product at the surface, oxide film at the surface of the steel bar is sometimes desirable. So, generally they increase corrosion threshold by making that passive layer stable. So, the oxide layer that is formed over the rebar becomes stable. Nitrite acts that way, all right, and less reactive, they are less reactive. So, therefore, protect the steel, right. Okay. So, less reactive by reacting with Fe and producing Fe2O3. So, they might first react with Fe and then allow production of Fe2O3, thus anodic sites are protected. So, these are anodic inhibitors. Anodic inhibitors actually protect the steel by ensuring that oxides are formed, oxides are stable at the surface of the steel. So, that iron does not get dissolved, the protective layer protects it. These are called anodic inhibitors. Nitrites essentially does this job, they react maybe with the Fe, but then finally Fe2O3 or such oxides should be forming at the surface of the rebar, because it will break down, right, reacting with Fe and then producing Fe2O3 at the second stage, and thus protecting the steel. Opposed to this, there are some others which are cathodic inhibitors. Now, dosage are 10 to 20 liters per meter cube of concrete, as we can see. Amino alcohols, for example, coats metal surface with a monomolecular layer and also inhibit cathodic reaction, hence mixed inhibitor. So, the mixed inhibitor both protects anodic sites and cathodic sites. Rebar corrosion is an electrochemical process, and in the electrochemical process there are some anode in the rebar, some cathode in the rebar, right. So, the anode, if the coating is there on top of the anode, this Fe cannot dissolve, at anode Fe dissolves, at cathode cathodic reaction takes place. We will discuss this sometime later on when we talk of rebar corrosion. Now, amino alcohols coat the metal and therefore, inhibits the anodic reaction, but also inhibits the cathodic reaction, right, and hence mixed inhibitor. Now, what is the cathodic reaction? Cathodic reactions are essentially the reaction between oxygen and hydroxide with absorbing electron to form hydroxyl ion. So, if you can stop that reaction, that is cathodic reaction will be stopped, then anodic reaction will automatically stop. Somewhere in the circuit you have to break it. So, cathodic inhibitor reduce corrosion rate by inhibiting cathodic reaction, stops the cathodic reaction of oxygen and water with which takes electron to form hydroxyl ion. So, sodium hydroxide, sodium carbonate, ammonium hydroxide increases pH and reduces iron dissolution. So, they increase the pH and reduce, because already there is certain amount of hydroxyl ion in the system, no further hydroxyl ion can form. It reduces the dissolution, formation of more hydroxyl ion, and that is how they protect it cathodically. Phosphates, carboxylic acid, hydrazine, hydrates, etc. Hydroazoic acid is HN3, is hydrogen and nitrogen, So, I think it is NH3 is ammonia, this is HN3. So, thus hydroazoic acid and hydrazine hydrate is one of the compounds from it. But it has been observed that some may reduce the compressive strength. There are some side effects from corrosion inhibitors. So, therefore, they may reduce the compressive strength. So, they have not been not very popular, but still there are some available and then can protect or can protect the rebar to certain extent, right, but they have their own negative effect. So, that has to be remembered. Waterproofing admixtures, they reduce the capillary absorption, thus lowers permeability and of hardened concrete. These admixtures, when you add to the concrete system during mixing, in the later stage they act on to the capillary pores in some manner or other and lowers the permeability of hardened concrete. They can be of this kind, like pore blocking treatment, pore blocking treatment or hygrophobic pore lining treatment. So, pore blocking treatment or hygrophobic, that is water repelling pore lining treatment. Now, hydrophobic property is essentially because of the contact angle between this material and water. Water and normal surfaces of concrete or many other things, glass, let us say, it is 0, contact angle is 0. So, water is a wetting liquid for this kind of material. Surface tension properties, I think we discussed sometime, or we may be discussing sometime later on. So, the surface tension properties, okay, just let us quickly we can have a look at this. It will be something like this. You see, water, you put it in water, water spreads like this. So, the contact angle, this angle is 0, this angle is 0, but if you look at mercury, mercury on the other hand will form some sort of bubble. This angle is 140 degree with glass. So, therefore, mercury is a non-wetting liquid. So, this we call as contact angle. Now, contact angle of water with surface is contact angle of water with most of the surface is 0. Contact angle is 0, but if I can make it, if the surface changes, let us say waxy surface, wax on a surface, contact angle with water which all changes, contact angle of water becomes greater than 90 degree. So, therefore, in a waxy surface you find that water possibly is water is possibly not spreading easily, not spreading. So, it is forming some sort of a bubble like mercury does in glass. So, therefore, this hydrophobic pore lining uses this principle. Hydrophobic pore lining uses this principle. Pore blocking is simply blocking the pore. Dosage may range up to 5%, right. So, these damp proofers are based on fatty acid, oleic, caprylic, stearic acid, etc., react with hydration product and block. That means, they will react. So, pore blocking product will react with substrate, mainly the calcium hydroxide, and produce CHS like product which can block the pore. So, if this material are added to the concrete, they can come at the they should be able to migrate to the capillary pores at the surface and react with the substrate itself later on to form such products which will block the pore. So, fatty acids like oleic, caprylic and stearic acid, etc., they react with the hydration product and block. Wax emulsion from hygrophobic pore lining layers. Wax emulsion forms hygrophobic pore lining layers, and then of course, calcium and aluminum stearates. So, they form hygrophobic pore lining layers. So, now this should do what? They when they are coated onto the capillary surface, they come onto the capillary surface, the contact angle of water has changed. So, water wants to, when water is trying to enter, when water by capillary suction, the ingress of water by capillary suction becomes then difficult, because mercury you cannot, like mercury you cannot force into, mercury you just do not go on its own into any pore, any capillary, you have to force it. So, here also on its own, once the surface changes, it becomes hygrophobic, liquid water cannot penetrate into it, you have to force it, but vapor can of course move. So, these are hygrophobic lining. There are varieties of other materials in this line of course, which does the job, but then the generically there are two types, one is hygrophobic pore lining and another is pore blocking treatment. All right. Then there are shrinkage reducing admixtures. You see, drying of concrete results in lowering of capillary meniscus, and since capillary meniscus will lower, the stress is introduced due to surface tension forces. You see, surface tension forces would tend to actually introduce a kind of stress at the capillary boundaries, because it is lower when the capillary meniscus is lowered. So, this surface tension forces, because it was at a balanced condition, now it has got lowered because some drying has occurred, and there will be some surface tension forces that tend to close the capillary and hence shrinkage. So, capillary will try to collapse under this surface tension forces. So, shrinkage do occur, and then of course, gel pores will also become empty. The water will move out from the gel pores subsequently, and there could be shrinkage and of concrete. So, drying there is a shrinkage of paste and hence the concrete occurs. Now, glycol and other derivatives operate by interfering with the surface chemistry. So, glycol and other some derivatives, for example, glycol and other derivatives, some of its glycol ether derivatives, they operate by interfering with the surface chemistry of air water interface within capillary, thus reduce the surface tension and consequently reducing effect of shrinkage by stabilizing the capillary. Well, if you look at it, air entraining agent also reduces the surface tension, but it has got a head and tail, one of them being hydrophobic, another being hydrophilic. So, hydrophobic side actually holds on, I mean hydrophobic sides actually traps the air bubble, but here this will not happen. This simply changes the surface tension at the surface tension of the water and water or air water interface at the air water interface within the capillary, and therefore, surface tension is reduced and shrinkage action is reduced. So, that is what it does, right. It does not have a tail which can entrap air. So, no bubble formation could occur, but only surface tension reduction will occur. So, this was shrinkage reducing admixtures. Then we have got alkali aggregate reaction inhibiting admixtures. Now, alkali aggregate reaction, as you know, some of the aggregates, some of the minerals present in aggregate can react with sodium and potassium hydroxides that would be present in cement water system, because sodium oxide and potassium oxides are present in cement, right. They are there in the cement usually in small quantity, and this might form sodium hydroxide and potassium hydroxide. Now, these ones will react with some silica minerals, forming alkali silica gel, and this gel can absorb water and expand in volume, result in cracking of concrete. We will again deal with this somewhat later on when we talk of durability of concrete, but then there are some inhibitors which can stop this kind of reaction. Of course, you have other means of controlling them, but inhibitors can also be used. For example, lithium hydroxide or lithium salts are effective in reducing alkali aggregate reaction, because sodium, lithium, potassium, they belong to same group, in the periodic table. So, lithium replaces sodium and lithium silicates gel, it is not gelatinous. So, this does not cause any expansion. So, air entraining agent also reduces the alkali aggregate reaction effect somewhat, because the air voids which are available, the expansion can be taken, and mineral admixtures are very effective in this, but mainly the like fly ash addition in the beginning or granulated ground blast furnace slags, they are very useful. Compounds like silane which are silicon and hydrogen compound like SiH4 or SiN and H2N2, this sort of formula, these are called silane. So, silane compounds and siloxanes are composed of units from R2 SiO, where R is a hydrogen atom or hydrocarbon. So, R2 SiO, H2 SiO to any other CH3 etc. So, these are siloxanes. So, silane and siloxanes materials, then silicofluorides together with this one, silicofluorides are the other material, they are found to be effective in reducing alkali aggregate reaction. In fact, silane and siloxanes are used in water repelling system as well, waterproofing system as well. We might look into this sometime in connection with surface coating and durability of concrete. So, but silicofluorides together with silanes and siloxane also are found to be effective in reducing alkali aggregate reaction. Calcium phosphate prior to use also reduce. If you use calcium phosphate with the aggregate prior to their use, this also reduces the alkali aggregate reaction expansion. As I told you, lithium reacts with alkali silicate to produce insoluble lithium silicate. So, this does not form gel and therefore, lower expansion, and they also provide with high valency cations to neutralize the osmotic pressure, because the pressure which causes cracking has something to do with its osmotic pressure in the system. We will discuss about that sometime. So, lithium in a second way it acts is it provides with high valency cations to neutralize osmotic pressure. So, that is how alkali aggregate reaction can be controlled by use of this kind of inhibiting admixtures, alkali aggregate reaction inhibiting admixtures. Silicofluorides, silanes, siloxanes, water repellent, as I told you, they are also water repellent and they allows air entrainment, hence able to reduce swelling due to water ingress and gel formation. So, they are used in water repelling, as I told you, waterproofing system. Calcium phosphate interferes with the dissolution process of silica and gel formation. These are some other material used for alkali aggregate reaction inhibitors. Some lithium salt, but reduces the strength, silane etc. has no such negative effects. They are used as water reducing agent as well as can inhibit the, and there is another side of it. Since they can reduce the water ingress, water ingress is a must for alkali aggregate reaction. So, that is another effect of silane, silicofluorides and siloxanes. I think that is what finishes our discussion on chemical admixtures. So, in total what we have seen is, we have seen actually water reducing admixtures which in more detail than any other admixtures, because they are in the last two lectures actually we have seen, because they are the one 60% of the admixtures are these ones, they are the most common one. Then follows accelerator, retarders, and we also looked into air entraining agents, corrosion inhibitors, shrinkage reducing admixtures and alkali aggregate reaction inhibitors etc. So, I think with this we just finish our discussion on chemical admixtures. In the next lecture we will look into mineral admixtures. Thank you very much.